about creating asynchronous applications using virtual threads. And this is a very fundamental shift in Java in terms of where we are going. And to me, if you look back at the time of the evolution of Java, you can pinpoint when there was a significant change in Java in terms of how we would do things very differently moving forward. And of course, the birth of Java itself was that. I remember the time when Java was introduced 28 years ago, 29 years ago. And I used to be a C++ programmer back then. And to know about this thing called Java, it's like, what does it do? And Java 5 was a very big change to Java. Because what Java 5 did was it introduced this concept of executor services. And you can manage a pool of threads much more easily and schedule jobs using executor services. So that streamlined how we did multi-threading. In addition to that, Java 5 also introduced a number of classes that performed operations related to concurrency. So Java 5 was a huge change back in time. After that, I would argue Java 8 was a huge change. Because in Java 8, we had the ability to do functional programming in Java. And that fundamentally changed the way we would write code with Java. But in all the things I mentioned so far, you had to write code very differently for you to benefit from the features of Java. You had to write code to use executor services. You had to write code to make use of the functional API. Those are definitely important, very exciting, but a more recent change is very intriguing because you get benefit of it, but you don't have to make a lot of changes to code. That is the even more fun part. I mean, isn't that awesome? You get benefit without doing work. Who doesn't want that, right? So this is like you can get the benefit, but you don't have to do as much work because they have taken care of doing all the work for us. So let's understand what that is in here. So what I'm going to do here is to talk a little bit about threads, talk about virtual threads. We'll look at the behavior of the code with threads and virtual threads. And then we will turn that around into a little example. The example I'm going to show you today is not very different from the example I showed yesterday, but with a small twist. And we'll understand how we would more practically write code with it in general. So let's dive in and take a look at what this actually means in here. So one of the very first questions I want to ask is, how many threads can I create? This is also known as a bad question. That's not a good question to ask. Because if you say, how many threads can I create? That's like asking, how much food can I eat? That's a really bad question to ask. A better question you want to really ask is, the question here is, how many threads, you could say threads, should I create? So there's a big difference between the two questions, right? So it's not about what you can, it's about what you should. And both in life and programming, just because you can doesn't mean you should. There are times when there are things you can do, but you should have the wisdom and the restraint not to do it. So the question is, how many threads should I create? Now, one answer you will hear immediately from people is that it depends on the amount of memory that you have. So the amount of memory limits what we can create, what we are allowed to create maybe, right? Pardon me. So that's one thing you can think about. But as it turns out, that is true, but not entirely true. I recently worked for a company as a consultant, and I really wish I had found them earlier in my life. Because almost every question I would ask them, they would answer back with another question. But working with them was like Christmas every day. I'm like, where have you been before this time in my life, right? So one day I asked them the question. We had a developer machine. I said, that developer machine, how much memory does that have? And their answer was, oh, that machine only has 1 terabyte of memory, But if you need more, please let us know. I was like, yeah, thank you, right? I mean, that's a beautiful question to ask, right? If you want more, we'll give it to you. Then I asked them, how many cores does this developer machine have? And they said, that one only has 1,000 cores. But if you need more, please let me know. I'm like, yes. This was, of course, you can have as much memory and as much resource as you want. That's because it was government funded, right? So you can have a lot of taxpayers' money. So the point really is, we can keep increasing the amount of memory we have on this application. With 1 terabyte of memory, I think you can agree, you can create a lot of threads, isn't it? That's not a problem. But as it turns out, we have to be careful. So the case in point, I was working with my good person on the team, on the client side. Remember, I'm the consultant who got hired into the project. And we had app code that was running, and it used to take a lot of time for it to run. When I say a lot of time, an application would take 12 hours to run. And they said, 12 hours is too slow, because when somebody comes to work, they make a change to the data model, and then they can have to wait for the next day to see what happened. So they said, if we can get the result twice in a day, we are happy. That will be a big improvement, right? So they can come in at the morning, fine-tune the model, look at the result in the end before lunch, fine-tune it one more time, look at the result before going home. That would be a good improvement. So we said, okay, let's work on making this run faster. But of course, if you're going to work with a code that's going to take 12 hours to run, you don't even know if it works or not, if you work with that magnitude. So my colleague at the client side, a very smart guy, he gave me a smaller data set and said, this is a good sample. If you can make this work faster, then we can see that the bigger model will work faster. Great job. So we took the little sample model, we ran it. It took 30 minutes to run. So the job given to me was make it faster. So I'm running it sequential. It's taking 30 minutes to run. And I made it parallel. And I showed it to my colleague and said, notice that. And we have 1,000 cores on the machine. I created 1,000 threads. And what took sequentially to run 30 minutes now takes 5 minutes to run in parallel. And I was like, can I pat myself on the back? Isn't that awesome? But he was not a person who could be pleased too easily. He said, 5 minutes. I'm like, yeah, from 30 minutes, we brought it down to 5 minutes. And he said, how many threads are you using? I said, 1,000 threads. He said, make it 2,000 threads. I said, no, we don't do that. He said, I'm paying you and I'm telling you to do it. It's like, okay, you're the boss. So we made the thread to 2,000 threads. Now what happened? The code that took 30 minutes to run sequential and 5 minutes to run parallel with 1,000 threads now took 90 minutes to run with 2,000 threads. And he said, what happened? I said, greed happened, right? You want to push this, right? Keep going further. Put more threads on it. So what happened? When you put more threads on it, your throughput goes down. Why would it do that? As it turns out, so the question we want to ask is, what's the number of threads we should actually create? Remember, the call here is should, not can. As it turns out, there's a formula you want to think about. And the formula is the number of threads you are allowed to create is equal to the number of cores divided by, you can say, 1 minus what is called the blocking factor, where the blocking factor is 0 less than or equal to the blocking factor less than 1. It cannot be equal to 1. Equal to 1 is deadlock. It's not going to move. So the number of threads is less than or equal to number of cores divided by 1 minus the blocking factor. What is the blocking factor? Blocking factor is the amount of time your task will not use your CPU because it's performing an I/O operation. And when it's performing an I/O operation, it's got to just wait for the I/O to complete. It doesn't need the CPU. For computationally intensive jobs, the blocking factor is equal to 0 because it's churning, right? Number crunching. So what's the blocking factor? 0. It's using the CPU all the time. But on the other hand, for I/O intensive jobs, the blocking factor is anywhere from, greater than 0. So you can say 0 less than BF, blocking factor less than 1. So it's anywhere between 0 and 1 because usually it's got to perform an I/O. And when it performs an I/O, you're not using the CPU. So your blocking factor could be anything more than 0. So what does that tell us? It tells us for, in this case, computationally intensive jobs, not mobs, jobs, that's scary. So for computationally intensive jobs, what's going to happen? Number of threads is less than or equal to number of cores. Now think about that for a minute. If I have 100 cores on my machine, and if you're performing computation-intensive jobs, how many threads can you create on that machine? 100. You're like, wait, but let me tell you how much memory I have. What's your answer? It doesn't matter. You have 100 cores, you're computation-intensive, you should only create 100 threads. So as a result, that's only amount of thread you can create for this to perform. What if I increase the number of threads? You're going to lose performance at that point. On the other hand, you can say for I/O intensive jobs with a blocking factor of 0.5, number of threads is less than or equal to 2 times the number of cores. So if your thread is sleeping, your task is sleeping half the time, you can push it to twice the number of cores. You got 100 cores on your machine. If your job is completely I/O intensive with a blocking factor of 0.5, number of cores divided by 1 minus 0.5 is 0.5. Bring the 0.5 up, that's 2 times the number of cores. So you can have 200 threads that you can create. What if the number of cores, so what if it's an I/O intensive job with, let's say in this case, with, you can say in here, maybe blocking factor of 0.9. That means it's sleeping most of the time. It's mostly I/O bound, not much computation. You're looking at 10 times the number of cores, isn't it? Because 1 minus 0.9 is 0.1, pull it up to the numerator, that's 10 times. What that means is on a 100-core machine, you can go up to 1,000 threads. Now think about that for a minute. If your application is relatively small in terms of the number of users, that's not a problem. But what if your application has to support 3,000 users at the same time, or 10,000 users at the same time, or 20,000 users, or 100,000 users? What are you going to do? And if it's mostly I/O intensive, you're looking at maybe 1,000 cores, and if you want to support 10,000 requests, your cluster needs to have 10 machines on it, because your scalability goes down to the limit based on the number of cores on your machine and the blocking factor. So that's pretty grim, isn't it? But what causes this problem? The problem in this case is that when your thread is being executed, when your thread performs an I/O, what happens in Java? When a task blocks, the thread blocks with it. And when a task is blocking, the thread is blocking with it. And because the thread is blocking with it, if you want to do more tasks, you got to create more threads. And the more threads you create, those threads end up blocking as well. And at some point, you hit the limit of the number of threads you can create. And if you want more threads, you want to be able to process more threads, you got to come up with more machines on your cluster. And the more machines you have on the cluster, the more the expense you have to incur as well. And you got to send this money to the cloud providers every month. Now, why are we paying more to the cloud providers? You say, because you need more scale. The question is, why can't I have more scale with fewer machines? Why can't I have more scale with fewer instances? Oh, that's because threads really get stuck when a task is executing I/O operations. So the problem is vastly underutilization of threads. And that's the way things have been in Java, right? Let's think about this a little bit and see what the consequence of this is. So let's take a little example and play with it. I'm going to create a function public, let's say static void do work. And what am I going to do in the do work? All I'm going to do is try thread.sleep. Well, give it a sleep of 5 seconds and a catch exception, EX. So nothing really, right? So all the do work method does is it sleeps for 5 seconds. That's it. Now I come in here and say, let's say a max equal to, we'll start with a modest value of 10. So with the modest value of 10, I say for I equal to 0, let's say I less than max, I plus plus. And then what are we going to do? I simply say new thread dot start. And to the thread dot start, I'm going to provide a call to do work method. That's all I did. Then I'm going to simply say, just let's wait for a little bit, right? Just ask it to hang on. So we'll ask it to wait for, let's say about, let's make this 5 seconds. Let's make this 3 seconds. So it's going to take 3 seconds. We're launching those, and we're going to wait for 5 seconds. So nothing really exciting, right? And when we are done with it, we'll simply over here output done. So that's all we are doing, right? So we'll just display done. So let's see how this is actually going to go. So I'm going to go ahead and run this code right there. And I want to see what it tells us. And 5 seconds goes by, it's done. No big deal, right? But if you really think about it, what does this code actually do? Nothing useful. All it did was get into the do work and immediately sleeps. So this is completely not using the CPU at the time, right? But the problem is that sleep is so to say, a busy sleep, not in the sense of running a loop, but the sleep is going to hold the thread hostage. So your task is running, your thread is running with it, and the task says, hey, I want to sleep for 3 seconds. And the thread is like, oh, I'll just wait. And it has to wait for the sleep to be over. When the sleep is over, it moves forward, isn't it? So as a result, you're going to be using that thread in this particular case. Well, okay, but the good news is it finished. You saw it print done. That's nice when it said it's done. But what if I go back to this code right here? And I said, let me try 1,000 threads, right? Rather than 10 threads, I'm going to do 1,000 threads. So I'm running that code, 5 seconds goes by, and what does it say? It says, I'm done. Not a big deal, right? It was able to handle it. What if I say 5,000 threads? So I'm creating 5,000 threads over there, run the code, and on this machine, this is not a big machine. It's a relatively small machine, comparatively speaking. It said, I'm done. Now I say, give me 10,000 threads. So again, what do the threads actually do? Nothing really useful. If you were doing something really useful, at least we can say, okay, something is happening, right? So I go back and run the code this time with the 10,000 threads. Oh my gosh, what happened? Notice what it's saying. Out of memory error. Oh my gosh. And let's read more. Unable to create native threads. Possibly it's not even sure. That's how bad it is. Possibly, right? It's like, that's what happened. It's possible. I think this is what happened, right? Can you imagine that? It failed because it used up too much memory. You say, but wait a minute, didn't they tell us threads are lightweight? The word lightweight is relative. You may have a little child and you say, oh my gosh, you child, you're becoming heavy. It doesn't mean the child suddenly is 300 pounds, right? No. Well, the child is growing a little bit heavier, right? So the light and heavy are really relative terms. So threads are lightweight, except when they are not, because they require memory. So you created, I don't know, between 5,000 and 10,000, we had an out-of-memory error, right? So that's pretty grim, isn't it? I cannot go any more, but that's only because the memory limit. We're not even talking about the number of cores. On that machine, I have 8 cores. So that means if my job is 0.9, I should have really created 80 threads. So I was way over the limit already. That's why you hit the memory limit, way past the limit of the number of cores and the blocking factor. So that's pretty grim. Can we agree with that? So if you're going to be writing applications with this, you got to go to a cluster of machines. That becomes necessary. Why? Because of the limitations of the threads in Java. So what can we do about this? So this is where this idea of virtual threads really comes in. So keep that in mind. We had trouble with 10,000 threads. Just keep that in mind. We'll come back to it. We'll talk about this more a little later. So now let's think about this a little bit more. I'm going to save this example. We'll come back to this a little bit later. So what do? The problem is when your task blocks, your thread blocks. And when your thread blocks, you got to create more threads. This is quite unfortunate, isn't it? So what would be nice? I'm going to give you an example here so can illustrate this. But I'm going to give you this example for you in Kotlin so we can appreciate this a little bit more. And then we can come back to Java after that. So I'm going to write a little example in Kotlin just to demonstrate this, because I want to show you what non-blocking really feels like. Non-blocking simply means your thread should not block and wait. Your task says wait, and your thread says, that's okay, you can wait. I'm going to go do something else. So how do I do this? I'm going to write a function in Kotlin. Oh, by the way, before I write the function in Kotlin, I want to just mention this to you. I not only love Kotlin, but I like the people who wrote Kotlin even more. I think they are really good humans. I'll have evidence for you to know that they are not just great programmers, they are good humans. Because they tell you when you program, you just don't write code. You should feel good writing code. They want you to have fun when you program. So to define a function in Kotlin, use the keyword fun. They want you to remember, have fun writing code. So fun task 1. How do you not like a language that reminds you to have fun when you're writing code, right? So fun task 1. And what am I going to do here with the fun task 1? I'm going to print, and I'm going to say entering task 1 with, and I'm going to say thread, a thread dot current thread. That's what I'm going to write over here. So that is my entering. Then I say exiting, as you can see. So that's my task 1. Similarly, I'm going to write my task 2. Entering task 2, exiting task 2. Nothing really exciting, right? So I run the code, run, and here I say, over here, I'm going to say, right there, I will say task 1, and I'll call task 2, and then I would say called the 2 tasks. And then I will also, once again, print thread dot current thread. So we'll print the current thread information right in there, right? So I want to display that as well. So we'll say current thread. So far, so good. So now that I implemented that, I'm going to display that information. What is going to happen when we run the code? Nothing exciting. You look at this and it's like, gosh, it's boring. That's exactly what you would expect, right? So you enter task 1, exit task 1, enter task 2, exit task 2, call the 2 tasks. That's what you would expect, right? So I did what is called a sequential code. Nothing exciting. But I'm going to make one small change here. Import Kotlin x.coroutines.star. It has brought in the coroutines library right now. I run the code, nothing happened. But I go here and say run blocking. This says I'm the parent continuation, coroutine rather. I'm a parent coroutine. I'm calling task 1, task 2 and print, but I will not finish as a parent until the children come home. That's all it says. That's why it's not run blocking. The parent coroutine waits for the children coroutine to finish. You're not going to see much difference yet. So when I run the code, notice what's going to happen. It still says entering 1, exiting 1, entering 2, exiting 2, call the 2 task. Fair enough? But I'm going to go back to this and say launch. And I'm going to launch task 1, launch task 2. And now, what does the launch do? For a minute, I want you to think about that long time ago when you wrote a Windows program, desktop application, or a Swing application, or a Java FX application, or any application that involved UI. What did you do? When you click on a button, your code doesn't go handle the button event, right? Clicking on a button puts an event in an event queue. And eventually you pick the event from the event queue, run the button handler. Think of this very similar. When you call the launch, it just puts an entry in a queue and says, hey, run task 1, will you? Hey, run task 2, will you? I'm going to print. Are you done? Oh, no, my queue is not empty. I'm going to run task 1. Am I done? Oh, no, queue is not empty. Run task 2. Is there anything in the queue? No, you're done. So imagine this like a queue. So when I run the code this time, notice the difference here in the code. Well, that's not the difference I wanted to show you. So essentially, launch, L-A-U-N-C-H, right? Launch, not louch. Launch. So notice what is going to happen right here. It says, called the 2 task. Did you notice that? It printed the last line first. Why? Because it's non-blocking. Then it said, entering 1, exiting 1, entering 2, exiting 2. So we see the non-blocking nature. How many threads are we using? 1. But the thread was non-blocking. What did the thread say? I'll call this later, I'll call this later. Boom, it went in there, right? But I come down here and say, delay 1,000. And I'm going to ask it to delay 1,000. So I'm telling this thread to delay the execution over here. Now, when I say delay, I want the task to wait, but you don't want the thread to wait. Now, before I can execute this code, I need to do one more thing. We need to alert the compiler that this is a function that is going to be asynchronous. I do have a formal complaint, by the way. I do have a very strong complaint. I mentioned that I really like the programmers who wrote the Kotlin language. I really like them. But I wish they had called me. I wish they had called me and said, Venkat, what do you think? I would have given my opinion to them. I'm really heartbroken at this. You'll see why in a minute. Because you want to tell that this function is non-blocking. So what would I have told them? Let's call it non-blocking fun. Wouldn't that be cool? Not just fun, but a non-blocking fun. Maybe non-stopping fun? Would that have been nice? But they didn't think through the consequence. They called it, I'm telling you, they called it, really makes me angry. They called it suspend fun. Seriously? What were they thinking? Suspend fun. Do you agree? That's not a good name, right? Anyway, who am I to tell? So, suspend fun, and you say suspend fun. Run the code. Now what happened? When you look at the output, calling the 2 tasks from thread main, entering task 1, but did you notice we entered task 2. Then we exit task 1, and then we exit task 2. So that clearly demonstrates the non-blocking nature. It's like you, right? Let's be honest about this. You wade through the traffic, you get to work. This is not work from home day, work from work day. So you show up at the office. What's your first thing you do when you get to work? Let's be honest. You want to get a cup of coffee, right? So you drop your stuff, you go to that machine that gives you coffee, and you're angry. The coffee pot is empty. Who did this? Why would the coffee pot be empty? So I hope you don't do this, right? You don't turn on the coffee pot and you stand there, staring at it. Your colleague says, hello. You're not responding. Are you okay? You won't respond because you will not move until you get your coffee that you deserve. I hope you don't do that, right? You complain, you turn on the coffee pot, it's brewing coffee. You go to your colleague and say, hey, are you ready for the design meeting? Oh, I need a few minutes. Fine. You go turn on this email, it's downloading email. What do? You're reviewing your document. Somebody says, what are you doing? You say, I'm waiting for the stupid coffee machine to have coffee. And I'm waiting for my esteemed colleague to be ready for the design meeting. I'm waiting to view this email that's being downloaded. I'm reviewing this document. That is the non-blocking you, right? So you are non-blocking, so you are in the middle of 3 things at the same time. So if I ask the thread, what are you doing? It says, I just launched the task, I've entered task 1, I've entered task 2, waiting to finish those 2 tasks, but I'm in the middle of all the 3 things. That is the non-blocking nature. How does this actually work? The way this works is by using a concept called, so these are coroutines. But the coroutines use a data structure that can remember your current state and restore that state when you resume execution. That data structure has a special name. It's called continuation. So a continuation is a data structure. I'll give you the most trivial way to remember it. Imagine you're working in an office, you work Monday and Wednesday, somebody else works Tuesday and Thursday. So they realize you actually don't need an office. So you go to work on Monday, you have a little station, you do your work. At the end of Monday, you say, I'm not going to be at work tomorrow. I'll be back on Wednesday. So what do? You take your stuff, put that in a box, and you store it in the corner with your name on it. And you leave work on Monday. Tuesday, your colleague comes, they use the same space, they clean it at the end of the day. You come on Wednesday, what do? You grab that box, put the stuff on your table. That's your continuation. So a continuation is where you save your state so you can resume it back when you need to execute. That's a continuation. Now you say, can I use continuation? Yes. How do I use it? I don't know about you, but if you tell me to do stuff I don't need to do, I'll mess it up. I'll create bugs, I'll create errors, I'll create unmaintainable code. So these people are very smart. They said, we will give you continuation, but you cannot see it, you cannot touch it. It's done for you behind the scenes. But I know what you're saying. You're saying, yeah, but I want to see it. I will show it to you if you promise you won't touch it. So let's take a look just for a minute, if you don't mind, just to see how this feels like. So I'm going to say fun compute n. I'm going to simply return n times 2. Nothing really exciting, just a compute function, right? So let's just get back to that in a minute. So go back here, Kotlin C-JVM. I'm compiling the code, sample.kts. Take a look at the, well, actually Kotlin C sample.kts. Just compile that code. Take a look at the bytecode being generated. So Java P, and I'm going to take a look at the sample.class that got generated. What do we notice here? Nothing exciting. So what you see here, right there is the Function, well, where's the function compute? It should be somewhere, right? So right there. So right there is your function compute. What did it do? Nothing. It's a final int compute int, right? We send an int, got an int. Fair enough? Nothing really exciting, right? So go back here. This time you say operate. But I'll call this suspend operate. So the only difference other than the name is the lack or presence of the word suspend. That's it, right? So now, if I go back and compile this code again and take a look at Java P and look at the bytecode generated, what do you notice in the bytecode? What you notice in the bytecode is the compute function is exactly the way it was. But look at the operate function. It says I'm taking an integer, but my second argument, which you didn't see before, is a continuation. So that continuation is useful to store and restore the state when you're executing it. So continuation is a data structure that stores and restores the state. So what we just saw with that example is how the Kotlin code works behind the scenes in terms of providing the capabilities that we saw earlier. So back to the scheduled program. So back here in the Java code, we noticed that that thread didn't really do a good job. You create more than 10,000 threads, it blew up, right? This is where the concept of virtual threads come in. So what's a virtual thread? A virtual thread, a thread is a native thread, meaning it is created at the operating system level. So if you create 100 threads in Java, using 100 threads on the operating system level, they're native threads. But native threads, as much as they're lightweight, are expensive. So what you do is your native thread is here, but you call them carrier threads. A carrier thread is a native thread. But a virtual thread gets mounted on a carrier thread. And when it's not doing any work, it gets unmounted. And then later on, when it's needed, it gets mounted and it gets unmounted. So notice what I'm going to do here. I'm going to go back to this code that we saw a minute ago. I'm going to run that code with the number of threads being 10. It should say done at the end of 5 seconds. It did. That worked. But that was only, 10 threads, right? But I'm going to make one change to this code. The change is not a new thread, but a thread.start virtual. So start virtual, and I'm going to remove this start from here. This is one way to really create it, not the only way to create it. One way to create it. So I said start virtual thread, do work. Now I go back and run the code, and what's going to happen? I need to spell it properly. So start, So start virtual thread. So run the code. Let's take a look at what's going to happen. 5 seconds goes by, and you can see it says done at the end of 5 seconds, right? No problem. You say, all right, that's great. What if you have 1,000 threads? Remember, it was able to handle 1,000 threads. Can it handle 1,000 virtual threads? And the answer is, yeah. 5 seconds later, it says done, not a problem. What if I said handle 10,000 threads? Remember, it couldn't handle 10,000 threads, right? So if I uncomment this line, it would have failed. Let's go ask it to run right now. And it runs and says done, but did you hear that? It said, why don't you give me something more challenging? You're like, really? Fine. How about 50,000 threads? 50,000 threads, right? So let's say go for 50,000 threads. It not only says done, it says seriously, why don't you give me something more interesting? You're like, really? I'm going to go for 100,000 threads. Somehow I feel like I'm doing an auctioning here. So I say 100,000 threads. Guess what's doing? It says Done. Give me something interesting. Do you feel a pressure in your blood? Do you feel like watching this movie? Tom Cruise is climbing this building. His gloves falls off. Do you feel that way? Maybe not that dramatic, right? But you're feeling like, really? 100,000 threads? Yeah. What if 1,000,000 threads? 1,000,000 threads. So let's go run it. What's going to happen? It says, seriously, dude, give me something more challenging. Done. How many threads can I create? How about the answer? As many as you like. Somebody said, what if I create 1,000,000,000? I said, you have some problems. You go back and find some help, right? Because the goal is not to create threads. The goal is to actually do some work. So the point is, you can focus on creating as many threads as you need. If you need a lot more threads, you don't need threads at this point, you need help. The point really is, there is no limit, artificial limit. Why? Because all those threads, what did they do? They did not use any operating system level threads. They were just little piece of memory. They were all parked and waiting. Your native threads, you need very few of them. So whereas you would have used 10,000 native threads in the other example, here you're using a few hundred threads at the native level. So it's able to handle it properly. So far, so good? Okay. You say, all right, that's all great, but we don't keep going around creating threads like that. We've been using executor services for a while. How would we do that is the question, right? So let's take an example here. So the example we're going to look at here is going to be, let's say, a public static, let's say void, let's say do work, takes an index, we'll say index. But then within this, I'm going to perform an IO. Oh, pardon me. Step back for a second to the code I showed you. What did you just notice? That the sleep is non-blocking. Sleep is non-blocking in Java now. Not earlier, but now. Earlier, when you called sleep, the thread will wait for the sleep to be over. Now when you call sleep, if it's a virtual thread, your task is sleeping, your thread goes to do other work because sleep is non-blocking. Why would you want sleep to ever be blocking? You don't want to hold the thread hostage, right? Similarly, a lot of other functions that perform IO are non-blocking. So I'm going to say try, and within this I say index plus entering plus thread.currentThread. Let's call that right there. So similarly, after entering, I'm going to say java.nio.file.star, and I'm going to say over here var result is equal to files dot lines and path dot off, and I'm going to just read the same file here, Java. You could do IO, you could do call to web services, what have you, an account. So then I say entering, and I'm going to say exiting. So I say exiting, right? Exiting. And then I'm going to simply exit because I got the result. I can print the result if I really wanted to, right? So I can say plus a little space and a result. So we can even see the result if you care about it. And of course, in this case, I can say a catch exception. And in this case, if there's an exception, I can print it. In this case, I'm going to just ignore it. So that's my code so far, right? That's what I'm doing. But I say var max equal to 10, for var I equal to 0, I less than max, I plus plus. And in this case, I'm going to simply say, oh, wait a minute. Forgot about that altogether, isn't it? So java.util.concurrent.star. So what do you typically do? You say executors is equal to executors dot new fixed thread pool of size, let's say 100, whatever that is, you can create it, right? So you created the executors, then you say executors dot, so executors dot shut down once you have started it. Then executors dot, and you're going to ask it await termination. And termination, how long do you want to wait? Time unit dot seconds. Wait for about 10 seconds, right? Well, it's going to complain to you. It says, ooh, what is the problem with this? Shut down, it says. Executors, and it says method shut down. So that's going to be on the executors, new fixed thread pool, who I've started it, not showdown, shut down. As I can say, I can type or I can speak, I cannot do both, but that doesn't stop me from doing it. So shut down, right? There you go, that's much better. My eyes are seeing it. Oh my goodness. It says interrupted exception must be caught or declared to be thrown. As experienced Java programmers, we know exactly what to do. So essentially, in this case, we are launching those threads, right? So here I'm going to say executors dot submit, and I'm going to say index equal to I, and I'm going to submit here, do work with that index. So we are asking it to execute that 10 times, as you can see. So if I go back here and execute the code, and I'm going to sort it and pull it up and take a look at the output, what do we notice in here? You can see that you entered and you exited, that's thread 1, thread 2, thread 3, thread 4. What we notice is the thread that enters is the thread that leaves, right? So that's basically the default behavior that we notice. But you don't want this to be blocking and waiting, so what do? We want to use virtual threads. Now, before I go to that example, I apologize to you. I'm going to say something very gross. If you're a person who doesn't like hearing gross things, you may want to close your ears. If you have children in the room, I don't think they are. If there are, close their ears. Or if you really don't like it, step for 5 minutes, come back. Because I like gross examples. The reason I like gross examples is, there you go, wise people, right there. That's exactly what I was saying. I love it. I love it. That's civility. I completely agree with it, right? They're like, nope, dude, no gross for me. Unlike you, they want to sleep tonight. You guys are all messed up because at 3 o'clock, you're going to wake up and say, oh my dear God, there's another person following it. See that? Because at 3 o'clock, you're going to wake up and say, I wish I did not hear this from Venkat. If Dilip is here, going to complain to him. It's like, you should not invite this guy again. He's saying gross things. I warned you, right? Virtual threads. Oh, I like gross examples because you never forget them. Virtual threads are like... She's even rushing. Let me give you one more chance. All right. Virtual man, tough crowd. Virtual threads are like Q-tips. Yeah. Somebody takes a Q-tip, uses it to clean their ears, and they ask you the question, should I save this? What would you say? Oh my dear God, throw that in the trash can. Why would you even think of saving a Q-tip, right? Virtual threads are like Q-tips. Don't. Too late. He is going to report to HR. You sent me to this conference. Now I am tarnished for life. Now I don't know if you'll think of Q-tips when you see a virtual thread, or you'll see a virtual thread when you see a Q-tip. That's your choice. But you should not pool a virtual thread. It makes no sense. Why would you pool a virtual thread? Virtual threads are use and throw like Q-tips are supposed to be. So don't try to put that in a pool. Well, if we don't put that in a pool, how do we use it is the question, right? Let's find out. She came back now. Awesome. You're safe. That's good. Nobody will tell you what happened here. So java.util.concurrent, oh, actually it's all there, right? So executor service dot, and what are we going to use? Executors dot, pardon me. What do we notice? New fixed thread pool, right? That's what we used a minute ago. But did you notice this beautiful new function? New virtual thread per task executor. New virtual thread per task executor. What that means is every time you schedule a task, you get a new Q-tip, right? So every time you schedule a task, here you go, a new one. Don't worry about the other one. This is brand new for you. You can use this, right? Toss it out. So that's basically what we have here is new virtual thread per task executor. So let's close that. Let's go back here to the code and notice what I'm doing. Just take that one line. That's all I did. Just that one line. And I say over here, new virtual thread per task executor. So you replaced your pool of threads with something that generates a virtual thread for every task you submit. What I love about this API is you can take your existing code with almost no effort. Would you agree? That one line, how much time does it take to change that one line? It doesn't matter. You don't tell that to your boss. You tell the boss, changing code to virtual thread is a lot of work. It only works by the beach. So I need to take a few weeks off and think deeply and make this work, right? So you can make that change right there. Let's save that away and go back and run this code again. Let's take a look at the output right now. And what do we notice? Notice 1 and 4. Notice 2 and 5. Notice 2 and 3 and 7. Notice 4 and 6. Notice 5 and 2. Notice this 2 is the same as this 2 here. So that's the mounting and unmounting that we notice. But the nice thing is you are creating a thread on demand when you need it. The native thread, the career thread, is behind the scene. The virtual thread is what is executing your code by mounting on the career thread. But the minute you are performing an I/O, it says, let go of the native thread. Your native thread jumps over and executes another task, and then is pulled back in. So you're just generating a virtual thread for every task you run. And the beauty of this is, as you can see in this example, is that we're not stuck with that particular thread to execute. And we didn't have to change a lot of code. We are still using executor services, But the executor services API has been nicely evolved so that your code that is using executor service, you are saying, hey, I want to switch from using threads to virtual threads. What should I do? Don't mess with the code. Just tweak the executor service to use virtual threads, and off you go. So that brings up the question, when should we use this approach? So some do's and don'ts. The first do and don't. Do not pool virtual threads. It makes no sense to pool virtual threads. So if somebody says, why shouldn't I pool virtual threads? Just buy them a box of Q-tips and they will understand it, right? So it makes no sense to pool virtual threads. That's the first thing. Second, if your task is I/O intensive, you can use virtual threads. If your task is computation intensive, it makes no sense to use virtual threads. Why? If it's computation intensive, it jumps in and is using the CPU continuously. How many times will it mount and unmount? Once. When it comes in, it mounts, it stays there until it's done. So you made no use of a virtual thread, except it's overhead in this case for no good reason. So if you're dealing computation-intensive jobs, don't use virtual threads. Use regular threads. If you're performing I/O operations, then use virtual threads. It is not a great idea to do new thread everywhere. Similarly, don't do thread.virtual thread unless you are just prototyping, experimenting. That's a great time. Why bother to do anything more? Just like I showed you the example of it. But to do anything serious, you're more likely going to use the executor service because that makes a lot more sense. So that is the whole idea. Was that useful? That's all I have. Thank you.